So we talked about this measurement of rates and how rates can be measured and how they are reported. So we have this rate, this numerical value associated with how fast the reaction is going at the moment. And one of the things we know from our simple observations of reaction is that the more stuff you have, the faster the reactions go, usually. Right? So there's a relationship between concentration and rate. And so it turns out that there's a simple mathematical formula that connects the rate to the concentration at a given moment. You plug in the concentration and you could calculate the rate very simply. Right? This is called a rate law. The rate law has the very general form: the rate is equal to some constant, small k, times the concentration of one of the reactants raised to some power, times the concentration of another reactant raised to another power, etc., etc. And we always write this with respect to the reactants. And so for a reaction A plus B, we would write the reaction for those. The order raised to some power, this power relationship, the order is not necessarily related at all to the stoichiometry. Unlike equilibrium, we could generate an expression that had concentrations raised to powers, but that's in an equilibrium. In a rate, these orders are always experimentally determined. You don't know what they are. All right, we talk about how this is first order or second order or third order, depending on the coefficient that's there, the numerical value that's there. All right. So the order is how, it's something called molecularity. It's how much those molecules impact the rate. And for us, the orders are going to be first order, second order, third order, or zeroth order. In fact, you very rarely see anything besides first order, second order, and zeroth order. But you can have fractional orders. You can have fractional exponents and things like that. You can have, so it just happens, but it's not common for what we're going to see. Not every component in a reaction will necessarily show up in the rate law. So you'll have 3 reactants, but only 1 or 2 might show up in the rate law. Again, you don't know. It turns out that you have to experimentally determine, and it has to do with the way the molecules are interacting. You do not know, and so it has to be experimentally determined. And there are 2 or 3 ways to experimentally determine them, and we're going to talk about one of them after we go through some examples with the rate law. And so this rate law can be expressed a number of different ways. So you determine the rate by measuring the effect of the changes in concentration as a function of time. Once you know that this is a rate law, we can easily figure out what the constant is. Right? A first order reaction, the rate depends on the concentration. We call that a first order. And so oftentimes the order is not shown. So this would be first order with respect to C2H6. The order here is first order, and so we show up as a 1. There's an implied 1 in this reaction. So if you measure the concentration, and you measure the rate, you could determine the rate constant. Then, given any other concentration, you could use that same constant to at a particular temperature, that value will be constant, and so it will just translate directly to the rate. Notice in this reaction there are 2 N2O5s in the stoichiometry, yet it is still first order with respect to N2O5. That tells us about how the molecules are behaving. The rate law is an equation that relates the rate of reaction to the concentrations. And we talk about the individual orders, the order with respect to A and the order with respect to B, but when we talk about the overall reaction, it is the sum of those 2 values. So for instance, if this was first order with respect to A and first order with respect to B, we would say that's the second order overall. Second order with respect to A, first order with respect to B, that would be third order overall. That's the overall reaction. Okay, so it's what would be the order? So the order for this reaction would be third order or first order or what have you. Right? Here's a very typical problem. What is the value of the rate constant if the reaction is second order with respect to A and first order with respect to B? And has a rate of yada yada yada. Okay, and so what this looks like. So what this looks like is we just have to extract the information from the problem. All right, so we start with the generic form of the rate expression. Rate is equal to the constant. Again, oftentimes this is forgotten. These are equalities, and if you don't solve them like equalities, they don't easily work for you. Constant A, constant B, and we find that they tell us the order. They say it's second order with respect to A, first order with respect to B. And then they tell us a bunch of other information. It is 0.333 molar per second for the rate. K, the molarity for A is 0.333 molar squared. Molarity for B is 0.500 molar raised to the first power. And then we just rearrange and solve. Right? The units work out for this because of the units at K. So let's actually solve that. 0.333 molar per second divided by 0.333 molar squared divided by 0.500 molar to give us the value of K. And the units for this would boil down to molars to the -2 seconds to the -1. Right? The units are less important, as you'll see. Traditionally, we just state the rate constant for the given reaction without actually including the units. Right? So we can solve that quite easily. 6.06. So relatively straightforward. So let's try the same setup with a slightly different problem. Now, rearranging and solving for K is usually one of the steps you have to do. But there are others. I believe this one is pretty much exactly the same, solving for K. Right? We're going to start with our general rate constant expression, K, blah, blah, blah. They say that this is first order with respect to A. First order with respect to A, second order with respect to B. Even though the stoichiometry is different, this too has nothing to do with the rate law. So focus on the information given. They give us the rate expression. They say, here's the rate law. That's the best case scenario. It means we don't have to do much work for it. They say it's first order with respect to A, second order with respect to B, solve for K. Same idea. They give us the rate, 0.500 molar per second. They give us K. They give us the amount for A, 0.100 molar, and B is 0.200 molar squared. Again. And then plug and chug and solve. Right, I'll let you rearrange and solve this for yourself. The value I get is 125. And the units for that would also be molars to the -2 seconds to the -1. Okay. All right. Again, don't fret over the units. The units drop out due to the complementarity of the units here. Right? The constant is given those units to allow us to get this molar per second as a rate out. Right? So very easy, very straightforward to solve for K. But once you have K, you can use it to predict the rate at any concentration. You have the following rate law, same rate law in this case. If the concentration is 100 molar, and the rate constant is 0.500 molar second squared. What concentration does B need to be for the rate to be 0.1 molar per second? We're trying to shoot for a 0.1 molar per second rate. Once again, we're given 3 out of 4 of the variables. They're told, they tell us what A is, they tell us what the rate constant is, they tell us what the rate is. All we have to do is solve for B in this case. So let's do it. The rate is given as, and so they give us the rate of 0.100 molar per second as our target, and they give us K, 0.500 molars to -2, seconds to -1, and they tell us the amount of A, 0.100 molar, and they ask us to solve for B. And so we can plug these values in. 0.100 molar per second divided by 0.500 molars to -2, seconds to -1 times 0.100 molar will equal B squared. And then we can solve for B should be equal to 1.41 molar for this to be the right speed. Now we can check that. We can take this and plug that back in, and we should get 0.1 molar. So let's do that. 1.41 x squared times 0.1 times 0.5, and it should gives us the right value. So rate constants are fairly easy to check too. Plug the values that you get back in, pick whatever the conditions are, and solve. So that's rearranging and working with a rate law. Right? Given a K, you can calculate a rate. Given concentrations, it's very useful, very smooth to do. All right?